Hi everyone. My name is Chip. I'm currently in San Francisco, and I'm extremely excited to join the event. So I was just telling Rivati that I really love Toronto. Some of my very good friends live there, and people keep telling me that Toronto is like Silicon Valley for good people. So yeah, I'm really excited to go. But I'm really sad that it's an online event. So, but I'm still hope to actually get to know some of you. Um, I'm from Vietnam, and I have an accent. So and when I'm nervous, I tend to talk really fast. So if you don't understand me, like please slow down. Like please tell me to slow down, and feel free to ask questions online as well. And I will look at the chat and I try to answer the questions. So for today, I'm gonna talk about machine learning in productions. So it's a generalize from a generalizations from a thread I had on Twitter not long ago about like some of the myths that I encounter when I talk to people who haven't deployed machine learning models in productions. Um, okay, so here I'm gonna start by just like introduce a little bit about my background. It's not that extremely relevant. I start from a writing background. I published a few books, and then I went to Stanford thinking I could do I would major in creative writing, but then I took some computer science course and it was really fun, and I kept taking more courses until I just graduate as a CS major, and it is some product with some so I helped launch browser, a Google browser, which is now the second most popular browser in Vietnam. So for AML, I did some internships with Primer, Netflix, and I also was working with NVIDIA. So I was one of the team members of the applications team at NVIDIA, which is currently hiring. If you guys are interested in joining NVIDIA, I'm also like with Snorkel AI, which is a startup that came out of stealth in July this year. So if you guys are interested in learning more Snorkel, you can go to our website, snorkel.ai, because this is not a session on Snorkel, so we're not gonna talk much about it. But we are also hiring if you guys are interested. So for this talk today, I'm gonna try to cover four things. First is a difference between machine learning in research and productions. Just like two main points. Second is some of the machine learning productions myth, and the third and the fourth part, actually very short, is about the phases. For major phases of like adopting ML, and then the principles of machine learning system design. For the first part on machine learning in research versus machine learning productions. So for the biggest difference, I would say is a objective. So in research, people tend to have choose projects that focus on one thing. So when I was studying research, I remember my advisors told me that you should choose a project with a very defined, like a single objective, and which is often the model performance objective. So for example, like let's try this on this data set and try this technique, and so that it can achieve like state of the art performance on it. But whereas in productions, the objectives, you don't have one single objective. You can have like many different many different many different stakeholders in the project, and each of them has a different objective. So for example, you can have a machine learning team, and the machine learning team objective might be to build a model with highest accuracy. By the way, I have a lot of like puppy photos because they are so adorable, and I try to insert them in the talks so that people don't fall asleep. So you have the ML team whose objective is to get the model with the highest accuracies. You have a product team whose goal might be like to create a product with a fastest inference, because there have been a lot of research. I think that I read in specific is from Google and Booking.com, where they just say it's like a very small change in latency, maybe just like 5% increase in latencies can reduce the conversion rate by like a few percent, which might convert into a huge loss in the revenue of the company. So the product team might want a whatever models that give you the fastest inference. So it has a sales team. So the sales team might want the objective might be to sell more apps. So it might want they might want a model that's like to recommend you like better ads. And they have the manager whose goal is to maximize profit. And the easiest way to maximize profit might be just to cut costs by laying off the entire machine learning teams. So you think it's ironic, but it actually not. If you read about the layoff news from companies, for like Uber and Airbnb, you can see that the AI team is easily among the first to go when the company is in financial crisis. So the next difference is in computational priority. So in research, you trained model multiple times, like run a lot of experiments, but you usually only run the model on the test set once to report the score. Whereas in productions, you train the model, but then you have to do inference a lot of time. So like every time so users want to use a system, you have to make inference. So so which lead to different priority in research and productions. So before we continue, I just want to have a refresher on the latency and throughput. So I find the example of an ant carrying a leaf very useful to explain the difference between latency and throughput. So imagine have an ant that's carrying a leaf from point A to point B, right? So latency is the time it takes for the ant to travel the route. And the throughput is how many leaves it can carry in a given amount of time, for example, like a second or an hour or a day. So so if the ant carries one leaf at a time, so which in a systems in a computer system, you can think of it like it serves only one query at a time. So it is a real-time systems. Then low latencies also means high throughput. So that like it means that if it takes less time for the ant to carry a leaf, then it can carry more leaves in an hour, right? But then things get a little bit more complicated when you do things in batch. Like so now imagine that the ant is not carrying one leaf, but it tries to carry like 10 leaves. So that like the time it takes for an ant to carry 10 leaves might be twice as much. So the latency now doubles. But because now it can carry like 10 times more. So it means that like even though it takes twice as long, but it can carry 10 times more. So actually can carry more leaves in a given amount of time. So it actually has like high throughput. So in training, this is actually one of the points that people still I want to share with people in research, a lot of people debate about it, because more people don't think about like whether like latency or throughput, but just think about like what are the fastest things I can how can I receive the results like the fastest. So in research, you want to train fast. So it means that you might want to like batch things together. So it means that you have like high latencies, but also so means that you don't care about high latencies as long as it's high throughput. But whereas in productions, because latency is very important, you want to keep the latency as low as possible. So so instead of like trying to batch things together, like you don't want to like wait for like 100 requests to like make prediction on a service at the same time. You want to you want to like as soon as a request arrives, you want to process it as soon as possible. So they have low latency at the cost of having like low throughput. I know that it's fairly like twisting, so I hope that it makes sense. So here's the whole point that in research you want you are willing to sacrifice high latency so that you can high throughput to make the most out of the hardware. Whereas in productions you want low latency at the cost of like low throughput. So it means that in inference you might not want to like use GPUs or TPUs like fancy hardware to do inference because it's very costly to just use it to run one single, but you try to optimize it to run the most on one single CPU. Okay, so there are several other parts in the research productions with data, fairness, and interpretability. I think we have been written a lot about it, so you guys can look it up, or if you have any questions, feel free to ask me. So for the next part is a more slightly less technical but more exciting part is a machine learning productions myths. So the first myth is that we'll say like deploying is hard. So it's actually deploying is so people like tend to like scare or where they, oh, if you only do research like you didn't do ML in school and then you have no idea what it's like to like deploy a model. So truth is like deploying is pretty easy, like especially in the last few years, basically since 2016 there have been like an explosion of tools to help you deploy models. So it has been pretty straightforward. So you can just train a model, you can create endpoint. So now people are using a lot of things like fast API. You create endpoints and you can dump things on AWS and you can serve it. So deploying, and you have like tools like Streamlit that lets you just create a simple API for a simple app to serve your model. So I think like if you are familiar with all those tools, you can create in like half an hour. So if you want to deploy a simple model for the friends to play with, it's pretty easy. But deploying it reliably is hard. So the difficult part is not just to create endpoint and bring it to end users. The difficult part is that like how do you scale the system so that you can like handle a lot of queries at the same time? How do you like minimize latencies? How do you like know when something goes wrong and how you can like figure out what went wrong? So imagine how hard it is to like debug a machine learning model in research. Imagine it's so much harder when you have to like try to figure out what's wrong in real life when like so many people are using it. So the second myth is that you only have to deploy one or two machine models at a time. So I think it comes from the research mentality that you should really like be very focused and like pick a like well-defined problem to tackle. So you think that like, oh, so you choose like how to like so you choose one aspect of an application and try to focus on it. But in reality is that you actually have to you will likely have to have a lot of models at a time. So for example, think about Uber. So Uber will probably need a models to estimate the ETA, and then you need another model to like detect whether a transaction is fraudulent or not, someone is taking advantage of the system. You have another model to like detect to like estimate the number of so the demand, so that you can like calculate those so you can like calculate how many drivers you need to get and how to incentivize them. So you need another model for like price optimizations. So you need a lot of models already. But then you don't if with luck you don't serve the model in just one city. Like if Uber operates in like 10 different countries and they probably need like each like a set of models for different cities. So like if you have 10 different models in like 10 different countries and it's already 100 models already. So in reality, Uber has about thousands of models. Booking.com has about 150 models. And here is a talk from Netflix when they say like a certain task that your machine learning to tackle. So you have like so machine translation is actually one of the things that I was looking at with Netflix. So for example, like you have wait, I'm not sure if I'm allowed to talk about it. Okay, sorry, it was just about hardware. So we can think about like what Netflix needs machine translation for. So or you can predict churn. It's extremely important in every business. So churn, you think of like how to detect when a customer is about to leave you, so that you can like come up with incentives to like pull them in. So the cost of acquiring a customer is very expensive. Some VCs actually talk about like how the acquisition cost is a one thing that like breaks startups. So if you look at like IPO filing for Lyft, you can pre-calculate the cost for them to acquire users. I think it's in the range of like $100 or something. So it's very expensive. So you once acquire a user, you don't want to just like let them leave. So you try to like predict when they are about to leave, so you can like maybe like point you like this, hey, here's a discount, like you might want to stay. So you can use churn prediction model for like not only like customer but also employees. So the cost of like acquiring employees is very high as well. So like some companies also look into like when an employee like is thinking of leaving, so that they can like try to like incentivize them to stay. And also a lot of recruiting agencies also like use that model to like reach out to people. So I'm not sure if you guys know have this like if you have been working at a company for a year to even study, like get a lot of message from recruiters like, hey, like are you guys looking at something? So churn prediction model is like one of the largest common machine model in machine learning productions. Okay, so myth 3, if we don't do anything, model performance remains the same. So I think like it comes, I think a lot of a time you think about like how you just build like here, develop a model. Oh, wow, now it's state of the art, we are done. But actually it's not. So in productions, I think, so machine learning is part of software engineering, and software engineering suffer from this problem called like software rot, a bit rot. So I think it's really funny when I watch science fiction movies, and like like how people encounter like some technology from an alien civilizations like from 1,000 years ago, and it's just like dust off the dust, and they come in and turn on, and everything just works. So like if I leave my code for a year and I come back to it, then nothing's gonna work because the API changed, something is not supported anymore, and I just forgot like what did what. So software already suffer from that problem. Like if the lead software is not degrade over time, and machine learning model is especially like this problem for machine learning is especially worse because not only it suffer from software bit rot, it also suffer from what concept drift. So it trains the model with certain assumptions about the data, but the assumptions gonna change over time. So the users' behavior might change, culture might change, so the competitors might have different plans. So everything's like all the changes might require you to update the model. So you have very extreme examples. For example, like think about a restaurant pre-COVID. So pre-COVID, if a restaurant is busy, is a good signal because like a lot of people want to go there. But like during COVID, right? You don't want to go. A restaurant being a busy is a bad signal because you don't want to go to a busy restaurant because it's a chance you get catching like the virus. Or before COVID, like if people look for Wuhan, people really think about like tourism. But like after like COVID started, if you search for Wuhan, it's like totally different thing. So that's an extreme example, but like things can like a lot of things can happen like gradually just over time, or like can be seasonal, or like weekend, weekday, or like Christmas, not Christmas. So I think like for it's very important to detect concept drift in productions. It's also important to measure how bad the concept drift for the model. So one tip is that like you don't just train the model from all the data beforehand and just predict it like on the new data, but you try to like collect the data from maybe like 6 months ago, a years ago, or like 2 months ago, 1 month ago, and then test the current data to see how much worse it's got. So it's very likely that like the models are trained on the data yesterday, so when do the best on the data today, but the model trained on data from 6 months ago will do much worse on the when it tests on the data today. So myth number 4 is that like you would need to update some models as much. So it's so people tend to ask the questions like, so how often do you update the model, right? You think about like you read news about like maybe company update a major models like once every few years, and then somebody said like, oh, you pretty should update the model like once every 6 months or once every year. So I think that's the wrong question. You shouldn't be asking like how often should I update my model, but like the question should be like how often I can update my model. So I think it's one of the aspects of machine learning that I think that we can learn a lot from DevOps. So I think this is one of the here's a few numbers that you can get from like 2015. So even in 2015, Etsy was already deploying like 50 times a day. Netflix like 1,000 times a day, and AWS like every like 12 seconds. So when I say update, it can be like every push to the systems that are serving serving their users. So I don't think that we need to update machine learning models as much, but I think like every moment the model stays unupdated, its performance in a get worse, which in a hurt the bottom line. So I think we should try to update our models as fast as humanly possible, and so which means that we will need a set of tools that should let us like push updates without like interrupting the service. And also like not all updates are gonna go well, and even though like we can test our system like rigorously before deployment, there will there will still be things that like go wrong in deployment. So like you want a system, you want to set up tools or a system that let you not only update the model, but also let you roll back to the previous point of the system. Is possible. So I think like if so there are a lot of tools like already available for machine learning that existing in DevOps, and I think that a lot of people are trying to bring like DevOps best practices into machine learning, and I think it's a really great progress. So the myth number 5 is that most machine learning engineers don't need to worry about scale. So I think people tend to tell me when I talk about machine learning production at scale is that like, but like how many Google or Facebook or Netflix out there, right? It's only like one of them each. And most companies they don't have system to serve like hundreds of thousands of users, a million of users. So I think that's right. But then like just so just because most companies are small doesn't mean most engineers work for small companies. So even though there are very small numbers of large companies, they actually employ the large proportions of the workforce. So here's a pretty interesting survey from Stack Overflow. So if you look at this, like actually more than 50% of engineers work for companies with at least 100 employees. So that like if a company with so it's very likely that if you an average machine learning engineer will work for a companies that work with machine learning model at scale. So yeah, so everyone should learn about machine learning at scale. So myth number 6, that machine learning can magically transform the business overnight. So it's a myth usually come from project managers or managers in general. So I think it's kind of like how to like manage expectations for machine learning. So people think that like, oh my god, machine learning is such a hard thing that everyone is using it, Google is using it, Facebook is using it, it's incredible. Like if I use machine learning, my business can just like become like, I don't know, be sucked in money or something like that. And when it didn't happen, they go out and say, oh, machine learning doesn't work. So I think there's a recent article on Wire that said like only 11% of companies that have used machine learning have seen like sizable returns on machine learning. So I think like that number quoted our context is actually very misleading. So first is that like it's very misleading because I think there are many problems with it, but I think just one core problem here is that it doesn't take into account the maturity of the machine learning deployment cycle. So because machine learning in deployment is fairly new in the industry, so most companies are not mature yet in that regard. And the less mature you are in the process, the longer it takes for you to bring the model into productions, which leads to two things. The number one is that like it costs more because it takes more engineers. It takes more engineering time to do it, so it just costs more money. And so the second is that we have already gone over like the longer the model just stays still, it's gonna get decay. So the longer it takes for you to bring the model into productions, the less well it's gonna perform. And yeah, so which means that it's gonna cost you more and give you less return. So I think here is another survey by Algorithmia about the machine learning deployment timeline and machine learning maturity. So you can see this like the longer a company has deployed machine learning models, the less time it takes for them to deploy a model. So like for a company with like very sophisticated models in like productions pipeline, like almost 70% of them can get a model into productions like within 30 days. But like if you look into the company just starting into productions, you can see that that's like over 25% of them here. So it's like it takes like over 3 months, or like in some point like over a year. And if it takes you a year to get a model into production, some model is not going to do anything good. And I think that the hope here is that like as people, as more companies use machine learning, as we have more tools to help people bring more into productions, and because like if we have more discussion on best practices, the time it takes for people to bring more into production will be a lot less. Oh, I saw some question. Okay, I'm gonna go through this very quickly, and then I'm gonna address the question. So for phases machine learning adoptions, I think like as the first phase of like is before machine learning. So I think like if in the beginning, if you have a new problem, you don't even have to look into machine learning solutions. I think I realized this quote by Martin Zinkovic from Google. He wrote this amazing machine learning engineering rule. So if you haven't, so it's like 50 rules of machine engineering. If you guys haven't read it, you should really go and look at it. It's absolutely amazing. So he says like if you think machine learning will give you 100% boost, and a heuristic will get you like 50% of the way there. And here's some examples I'd like to show to people. So you know that like we all familiar with Facebook, right? And we know that Facebook newsfeed is like using like really complex algorithm to rank like which post people should read first. But here is a screenshot of like Facebook newsfeed when it was first launched in 2000 and I think it's 2006. And I'm wondering like, do you guys have any like guess on like why it looks what anything peculiar about this news feed? Anybody want to take a guess? Yes. So Andre said like, yeah, yes, it's sort of by time. So like when newsfeed was first launched, there was no machine learning at all to rank the posts. It was just like they were just ranked by pure correctly order. So I'm saying that a lot of products can be launched without machine learning, and then you can use the data collected from the product to actually train the future machine learning model. And then the next, so after we launch the product, right? And now the next phase is to use a simplest machine learning model. So, so I think like for machine learning, all machine learning models are hypotheses. We hypothesize that there is a pattern. There's a way to learn the functions that like take in the input and output the predictions, right? So we don't know if hypothesis is true or not. So having a simple models and see if they work help us first to validate our hypothesis, and that our data can help us get the path, like can learn the things that we wanted to learn. And the second is to validate the pipeline. So pipeline is extremely important. So it's another talk by Google at OpML. So when they analyze the 96 postmortems of like machine learning outages at Google, and they found out that most problems are not even machine learning, but they're caused by like some like engineering problem, some pipeline. So like it's a lot of problem with like distributed. If you work with a distributed system, like you want to do the data model in parallel, or you want to serve multiple users at the same time, it causes problem. And I think another very common problem that I see is in feature engineering. So it comes from like the difference between training and inference. So in training, we want to batch things together and do them. So you process data in batch, right? So you have feature engineering to like do all of them at once, do a lot of them at once, like maybe a lot of like samples at the same time. But whereas in inference, you process like example every sample. So you can see that like you have different code to process them in batch, and have different code to like process them one by one. So the batch one, you might use something like vectorization or something, and which might cause you problem because like you input a sample into the training pipeline, you get a different set of features. And then when you put the same sample into inference, you get another set of sample. So I think that it's very important to make sure that like different results of pipeline do exactly the same thing in both training and inference. And you can do that by like just inputting the same samples through training and inference to see if they output the same result. And I've seen a lot of people like getting different results from like training and inference. Okay, so the next phase is like after you have the simple models that they work, you can validate the hypothesis and you validate the pipeline. You can try to optimize the simple model. So you can like try different objective functions. You can try like different input and output setup. You can try like feature engineering. You can throw in more data at it. You can try something in ensembling. Like, you can do a lot of testing because it's simple model. So you can so you need a lot of like visibility into its working and choose the features just like work best for it. So I realized simple models, and I think we should really experiment with them because not only they help understanding which features are useful, like which data is useful, it also help us like act as baseline because like if we want a complex models later, they have to perform really much better than the baseline so that for them to be deployed. And also like you can also use input like you can select predictions from simple models to as input into more complex model. So a lot of companies do that and find it's like really useful. So the next phase is like when you go to like fully really complex machine learning model. And I just want you to say this like don't be afraid of rules based. I think and I know that in the last decade everyone is going to like deep learning and there's a rules based systems so like in the 70s. But I don't think that it has to be like mutually exclusive. Like you don't have to use only machine learning without rules. Like so rules based system can also act as like simple models. So for you to like for you to use that feature for the more complex model. Okay, so I think it's just like some of the principles are still work in progress and know that they need more elaborations, but I think the time is out. So I'm gonna try to write more about this. I'm gonna talk a lot more about this in my upcoming course at Stanford. It will cover more with more hands-on tutorials. Okay, so I think my time is up. I think there are some questions online. Yeah, thanks people for sharing the link. I see Sui shared the link about the Wire article, and Krishna says the link um, about the rules of ML. Yeah, and I think I also wrote about, I think Abhishek has a very has my link about the machine learning system design. It's a pretty simple version. Actually, I'm working on a lot more elaborate version of this. Okay, so I think the time is up. So I'm gonna like try to. So I'm gonna collect these questions and not sure how to best share with you. Yeah. Yes. Can you somebody said, can you show the side of your course? Can you guys send me an email for the questions? I need to run. Yes. Yeah, Twitter is good. Thanks guys. Oh yeah, so I think there's a questions I think you can answer like for reproducibility and performance comparison. How do you track which versions of training features are used, especially when they get updated periodically? So I think so I think like first of all, I just want to mention that the term reproducibility have different meanings in have different meaning in research and in productions. In research, when I say reproducibility is for other people to like validate or the results and also like to build upon it. In productions, it's mostly to ensure the quality of so that we can roll back to a different system and to compare across systems. So how the question is how do you track which version of training features are used? I think, of course, so I think it's combination like what we should versions in machine learning. So I think that people have different ideas. First of all, like they say like less less version data set, and I think we have a lot of tools for it. First of all, DVC, I think DVC is pretty great. We have also like experiment tracking, like TensorBoard and weights and biases. So you have like, so you train different models, and they're gonna like a version for you, like what is the setting, what is the settings for this model, and what is the artifacts we mean like learning curve and stuff, and what is the like the output, like the metrics, the performance of that. So I think that a machine learning system, you can't just like version different aspect of machine learning system. If you version machine learning, you have to version like all of them at the same time. So you have to version from like the code, you have to version the system, like what system you use. You use like a 2 GPU or like 20 GPUs, because we actually notice it's like our model can have different performance if you use like one single GPU or you run it on like multiple GPUs. You have to versions also like a feature on the data. So with like code, systems, data, experiment, yeah, and also the weight. And so you have to version all of that. And I think like there are systems for you to do that. So actually Snorkel actually let you do that. So because it's an end-to-end systems, we care a lot about allowing. So we care a lot about like allowing people to like understand what they have been working on and how to like keep track of different models and different versions. So yeah, so it definitely really depends on the tools you use. So I think one simple way you can use is just like make a copy of everything. So there are a lot of logging tools. So as you run a model, you just like make a copy of like all the code you run, and also like how you should structure the code. I think you should definitely structure it in a way that's that you can store. Maybe you want to set up in a YAML file or something. But it really depends on what tools you use. Okay, I think I will need to run now. Sorry guys. As you can see, my face is super red right now because I'm like very nervous. But yeah, feel free to send me an email or reach out through Twitter. Thank you guys.